Good morning, everybody. Thank you for joining us. So this is a nice, cozy audience. We'll have enough time for questions and any deep dive we need. Oops. We're already introduced. So Carol and I work in the data center group at Intel, and we're part of a research and development effort to create autonomous vehicles. And our learnings today are from that effort that we're going to share with you. And we've had help from Santiago, Conrad, Sundar, Alexander, and Ismo. So this has been a joint effort and something we're very excited to share with you today. So what kind of data volumes are we dealing with for autonomous vehicles? We can have anywhere from 1 to 20 terabytes of data per car per hour. So this is like huge volumes of data. And depending on the size of your fleet, you might be looking at about 1 petabyte of data a day. What changes here? Why the 1 to 20? You have different number of sensors, you have different resolution of sensors, you have different kinds of sensors, and that's what contributes to your data volumes. The stakes are high. We want our vehicles to be safe. We want our journeys to be safe, sound, secure. So those are the reasons for all this sensor pool that we have and the volume of data we need to analyze, and that changes the whole scope of how fast we need to work, how diligently we need to work, and what kind of computing power we need in the data center, and what kind of software stack we need in the data center. That said, let's see how we can speed this journey. Another pun intended in this driving journey. Today we're talking about hardware acceleration in this data center. Where all do we need inference? Hardware acceleration for inference. First and foremost, to create good models, you need good ground truth. To create ground truth, we've typically used humans in the loop who have gone and looked at lots and lots of images, lots and lots of LiDAR cloud points, so on and so forth, and they go manually, like labeling each pixel. This is part of a car, this is part of a traffic light, this is part of a street light. It's really time intensive, and there's several companies out there that provide this as a service, but it's still expensive. Intel itself has spent about $250,000 to label manually a small set of data. There are other companies out there, and if you had heard the keynote talk today, Tesla itself is using this whole manual labeling process to create its whole software. It's like, forget telling you like, hey, if there are raindrops on that windscreen, please apply the wipers. It says, let's just show them the images and say, here, these raindrop image, now apply wiper type of thing. So label, use wiper. So you understand now how important this manual labeling process is. But it's expensive. Can we speed that? Can we use some automated inferencing so that you can apply labels to pixels and then have a human go in and fine-tune those and fix a few pixels up there? Where else do we need inference? To meet government regulatory requirements. There's privacy considerations. The GDPR says you can't share images of people, you can't share license plates. Even when the data has to cross a country boundary, there's so many regulations. So this all affects how you can share data. And it's all about sharing these huge volumes of data so we can make better models today. So we need inference there to detect those faces, then to blur them, to detect those license plates, then to blur those. Yet another place where we need inferences in all that simulation work that has to happen for this digital car. When we're creating all these detection models, then the planning models, then the actuations, all that has that important piece of first that detection. So we need to speed inference in this data center. Well, a lot of car companies are now working on this, where Waymo and Tesla and all have been working for maybe a decade. So these car companies now that need this sort of research development data center need to accelerate everything to kind of catch up out there. What can we use to speed? Well, we can have better software, we can have more machines, and today we're talking about hardware acceleration. So let's take a look at the compute continuum. You have CPUs on one end, very fast, yes. They run at 3-4 gigahertz. They're very flexible, but can we get faster? Yes. You can go to the other extreme on the right and have special purpose hardware. Those are your ASICs. They're very fast, but they're fixed function. But today, where are we? Do we have everything as a fixed function? No, we're still developing models. We're still developing algorithms. We're still developing planning routines. So we're kind of in a space where we still need the flexibility of being able to program things. And that's where GPUs, FPGAs, and the Movidius chip comes in. How many of you have heard about the Movidius chip? Okay, 4, 5, 6, 7. Okay, those are the Intel ones. Don't count them. So our team itself, like, hey, we've acquired a new company. It's Movidius. They have this cool, visual compute unit. And we in the data center said, could we use it? It's really, really affordable. It's about $80, one little USB stick. And our machines are several $1,000s. Can we use that to accelerate our workloads? And that was how this whole journey began. Conrad on our team says, hey, how about we try this? And lo and behold, we started ordering a few of these. We got like 8 of them. We started using them. And that's this little blue guy. So today we're going to talk to you about FPGAs, something Intel has also invested in. We're bringing it in as a PCI device. We're also working on it as an integrated component on our chip. And we're also going to talk about the Movidius chip today. Okay, so let's take a little closer look. What does the FPGA give us? What does the Movidius chip give us? And what's in there to support them? So an FPGA device has logic blocks. It has memory, it has security, so you can't just load any model that's not signed, so that gives us some security when you're running it in a vehicle so you don't have a rogue vehicle afterwards or a compromised vehicle. It's programmable. What happened? Hey, darkness reigns. No, I don't think we need this. Yes, you can. Sorry. We have rescue. Did I do something? We are resilient. We are fault tolerant. We are prompt in our SLAs. Thank you. Yeah, we can go next down. Thank you so much. Okay, cool. I did wonder why it got suddenly darker. So back to where we were. So FPGAs have logic blocks, memory, you can have security. They're fast, they're programmable, there's software tools like OpenCL, but they're expensive. They're, in the thousands of dollars, a couple of thousands at least. And today we've used them in multiple applications such as network processing, switches, and telecommunications. So you can get those systems that 100 gigabytes per second type of stuff. So can you use it for machine learning? Yes, I'm sorry about that. The Movidius chip, it's also programmable. It has an SDK to help use it. It's so affordable that anybody can start using it, programming it, develop, practice, get familiar with it. And it's tuned for image processing, so that's one of its main use cases. That was how it was born and intended. So they use it in drones, in cameras, in augmented reality, and it is fast. And let me just give you a peek at how our data center looks. This data center that we developed for research and development that our partners are using, and they're using it for like 25 cars, bringing in about half a petabyte of data currently. So this data center is fungible. We want our resource pool to be useful for machine learning, for inference, for simulation, for parsing. When this data comes off the cars, there's huge volumes of data. We need to open those packets that have come off those loggers in the vehicles and then connect up all the dots, as you say, for the camera 1, the camera 2, the LiDAR 1, the LiDAR 2, whatever. So we want to be able to use this compute for all these sort of workloads, not having little silos that this is only for simulation, this is only for parsing, etc. We also, as part of this data center software stack development, wanted to be resilient and then dynamic. So if something is larger in volume, and this is the sort of stuff that Kubernetes provides you, the auto scaling, and if a container fails, it recreates one. We wanted it to be easy to use, so APIs to launch workloads. And definitely we want fast, and that's why we're here talking about hardware acceleration. So given this environment of ours as Kubernetes, and we have Spark, and we have Hadoop in there, which we kind of mentioned in the previous slide, over here we have Hadoop, HDFS, Ceph, all those goodies. We wanted all of these to work together. And that brings us to the Kubernetes device plugin. So Kubernetes has its core software, but wherever you have this vendor-related stuff, whether it's a GPU, an FPGA, and the Movidius chip here, they allow you to extend your workloads and leverage these new resources using the device plugin. The device plugin operates with the rest of Kubernetes, so it talks to your master, which does all the authentication, authorization, et cetera, and then it collects all the information about the different nodes. So when you have a device, you register it with the kubelet, with the node, and then that populates up into the master saying, I have GPU, I have this many units of GPU, I have this many Movidius, et cetera. So next time a workload comes that says, I want GPU, it'll know which node has it and then schedule the job over there. So we said, can we integrate our accelerators with the device plugin? So with that, I hand off to Karol.
Okay. Hi, everybody. So basically, our journey started with Kubernetes cluster. We're sitting on the Xeon nodes, bunch of nodes, and with available hardware like FPGA Area 10HX and some Movidius USB sticks. So the first question that we actually asked to ourselves is that if we can use all the things that we have here, all the hardware, just from Spark, as simple as we use Spark. So because one of the biggest advantages of Spark is that it abstracts away more complicated things that are done in the background. Yeah. So the answer was simple: no. Both of them didn't come with any support for Spark. Yeah. So the next question was, maybe if we can't use that from Spark itself, maybe we can just use it in the same program. So we had Kubernetes, we had Movidius, which has a Python and C bindings, API. We also had FPGA, which also had C API. And we wanted to use that with Spark on Kubernetes. So from version 2.3, we have support for Kubernetes on Spark. Unfortunately, after some tests, it went obvious that Spark support only for now Java virtual machine workflows. So if you want to use Spark on Kubernetes with Python or R, it's not a good idea right now. We need to wait for the full implementation. So the next question was what we can get from what we have without Spark for Kubernetes. Yeah? So as we got Kubernetes itself, we decided that maybe we could go with the more known way for us. Just expose some hardware as a service. Yeah? So we lost some things that comes with Spark, which are priceless, like data locality, but we still got things from Kubernetes. Yeah? So for example, if we have a health check, if we have liveness check, it can manage the access to the service. It can restart it. We can also provide load balancing, etc. So after some thinking, we decided that we'll go with a microservice approach. We just wanted to expose API by using gRPC and doing some preprocessing on images using OpenCV. So in all our solutions, which first one is the CPU, the second one is FPGA usage, and the last one is Movidius. We had the same overheads on communication. We just used gRPC, so it was like 3-4 milliseconds for each call. Even between nodes, it was the same. and like 16 to 30 milliseconds on data preprocessing, because we were sending compressed images, and microservice was responsible for decompressing them, resizing them, and preparing for feeding to the machine accelerator. Of course, this solution isn't the prettiest one. We managed to have some problems. So with FPGA, you have a big control on the model. So you can tune it up, you can test it, and actually you need to do that. Yeah, so if you get even generally available model, you need to modify it to fit your hardware. And the trade-offs that comes with that is that, for example, you have much flexibility when it comes to the data resolution. So you can use, for example, 9 bits on floating points. Yeah, you can use 16, 24. It depends on you. But it comes with price related on model accuracy. Yeah? So when you are tuning everything, you need to take that also into account. So it's also an important thing because you can't reuse your model with other hardware. You need to prepare your model for selected hardware. Okay, and regarding the model that we used SqueezeNet, which is very light on resources and plays well with FPGAs and with MoVideos. So for more complicated models, it could be a problem with using them with hardware accelerators, actually. So FPGAs are quite known, and MoVideos is less known solution. Actually, it weren't prepared for usage on the server appliances. It was mainly prepared for using with the low-power machines like Raspberry Pi for prototyping and for preparing for moving from MoVideos USB stick to something more embedded. So with that came some problems. For example, it behaves a bit esoteric. After model loading, it's metamorphosed into another hardware. Yeah? So it made some problems with containerization. If you take a look at the presentation, you will see that actually we almost removed all the things that make containers usable. Yeah? So all the security issues, all the barriers were destroyed just to run it with MoVideos. As we know, a new version of MoVideos SDK should resolve some of those problems. We still need to check that. And we are also aware of new MoVideos, which should go with 2 flavors, one PCI Express, so it should resolve all the problems that we had with USB stick, and also the new version of USB stick, which should perform at least one order better than current one. Okay. Okay, and very important from service point of view is that you can also, on FPGA you have one model, and changing that model is a quite big issue, yeah? So it needs some time. In case of MoVideos, actually we are supporting up to 10 models per hardware stick, and the changing of that models in runtime is quite light. So it doesn't need too much time, yeah? So here comes the results that we got. And as you can see, FPGA is the most performance one, is the fastest one. It still uses CPU for some layers, but even taking that into account, it's like 2 times faster than CPU. And MoVideos on this, when we compare it with other results, isn't so big, isn't so great. Yeah? But you need to take into account that these results comes without price. In our case, with a price tag. So if you take a look in the Xeon takes around 120 watts when running such interference thing, and costs around $600. when you take a look on FPGA, and this is Area 10 FPGA, a developer board costs around $4,500, yeah? And uses around 25 watts. So it's still an order of magnitude less than the CPU. And when you take a look on Movidius, even it's not so fast right now, when compared to using, for example, Raspberry Pi will take like 200 milliseconds, 300 milliseconds to do the same thing on CPU. Also, Movidius uses 1 watt for inference and costs only $80. So if you are comparing it to the performance per watt, or if you're taking a look on the price tag, Movidius is a good thing to test, to consider. Especially that you can, for example, add like 10 Movidius chip sticks on one PC. Okay. Okay. So some things we are used to for some things. So for example, with CPU, you are getting time sharing. Yeah. So you can say that you, for example, want only 10% of CPU core to use it. With hardware accelerators, it's a bit more problematic. You can't share them like that. You also are responsible for preparing all the implementation to make it thread safe, to make it usable by multiple clients, etc. So right now, it's not so easy to use like CPU or GPU, yeah? But we can put effort to make it easier. So when it comes to presentation, okay. So I'm not sure if you are, yeah. As you can see, we have here information that we should have available FPGA on this Kubernetes node. It's still 0, so it's not connected. So we are launching, so we are programming FPGA to act as inference accelerator. We are launching it as a plugin to Kubernetes. Right now, it's registered. It should be visible in the logs. Yes, it is. Okay, and here is inference. So this is how pod with microservice looks like. So with this plugin thing, we are getting for free ability to schedule and to demand resources which we want to use. So in this case, we are informing that we'll use FPGA. Okay, so pod creation. Yeah, the initialization is finished. And inference job on our test image. So the results could be a bit off because we scaled it to 1-to-1 without removing exceeding parts. So in our case, it's a golf cart after resizing, but it shouldn't affect the times used for. Okay, and Movidius neural stick. It's a very similar approach. Yeah? So we didn't use the plugin for that. We just used the native API. So it's running. And in that case, gRPC is quite effective way of communication. And the big advantage of that communication is that gRPC, when you define the protocol, creates bindings and all the stubs for multiple different languages. So you can launch this with C, with Python things, with anything else. So it won't be a problem. Okay, so it's obvious that there is a future work. So this is actually a first step to something bigger. So it looks like we would need to introduce a Kubernetes device manager for Movidius if we want to use it on the real workflows. It will be also nice to realize what we can do to have native support from Spark for more videos, because easy of useness is a big advantage of Spark. Yeah? And right now, it looks like hard work to get it working. Okay. And we also thinking about some scheduling things to decide, for example, if right now we want to execute this part of program with more videos, or just let it go and do everything on CPU. For example, more videos could be could have much higher load, and waiting for more videos could be not a thing for us. Okay. So, if it comes to conclusion, FPGA support is much more mature. It's not the golden solution, but still good. More videos is something that we can give a try, test if it's okay for us. Still, we need to do all the management and time sharing, etc., on our own. So it comes with a price also on developer side. So, Malini? References.
Thank you for being here. There's a bunch of references there. So we're still in early days of Movidius. Version 2 is already here. It's going to be 10 times faster at least. So where that FPGA gave you something at 3.4 milliseconds, you're going to get it at the Movidius price point and similar time. We definitely think, given this use case, I mean, the Movidius folks hadn't thought of this use case, so they're very happy to include us in their beta program. We're giving them feedback. We're saying some of the privilege escalations we needed are a no-no in this container world. But even that privilege escalation is kind of fine if you're in a data center where all your workloads are single tenant. It's not a shared cloud like maybe the Amazon or Google clouds, then it's perfectly fine. So you can get acceleration and meet your needs. Yet another thing that Karol mentioned was the scheduler enhancements that we should think about. Like, say you have a workload and you want to run it fast and you want to run it cheap. Do you wait for that hardware that can do it for you, or should you just take any hardware? I mean, if there's an FPGA free, take it, or just CPU, take it. So those are some of the things we should start thinking about in this space, be it for Kubernetes or Spark. Should you wait or just run anywhere type of stuff. So a lot of good stuff, and this all was born from our own need for high inference speed and a lot of it. So please give it a try. Thank you.